In the last video, we saw how we can constrain the GBM data in time and energy domain. We did the same with LAT data. We also saved their lookup files, and now we will move on towards the final step of performing the analysis, the data fitting. Um, as previously, I have loaded the N4 detector first because it is the brightest detector, then N3 and N8, followed by B0, and finally the LAT. The data for the LAT is shown here. So in order to do the spectral fitting, we go to spectral fitting and fit selections. Okay, let me enlarge it a little bit. So it's now asking for response files for N4 detector. So let's select that. Let's do the same for N3, N8, B0, and for that we will select the response file. Okay, let's accept the selections. Now these are the functions that we can fit on our data, but we will mainly be using power law, smoothly broken power law, band, Comptonized, black body, and then at the end we will see the effect of the effective area correctness on the fits. So let's first just do it with the power law. We'll go with set parameters and cstat as a fitting statistics, accept, revert to defaults, and then let's close this. Okay, the fit is performed. We have a statistics of 48,122. However, the fit is performed only once. So we will go to options, set fit repeat, and we will repeat the fit 100 times. This is just to make sure that there is no non-converging fit or slowly converging fit in it. Let's clear that. Go to redo last fit, accept, and then let's perform the fit again. Okay. Here in the fit display options, you can select the options to see count spectrum, or the photon spectrum, the energy spectrum, or the new FNU spectrum. And with these options, spectral model component, you can also see components when fitting multiple models. In order to save the results, we go to fit results and write result to file, and we will save it as pl.fit because we fitted the power law function. Save. Now let's add a black body component in it. So here we can see that the fit has gone from 48,122 to 64,33, a huge improvement in CStat. And we can also see it through the new FNU spectrum that the NAI detectors are now being better fit due to the additional black body component. So let's just save this, write result to fit, and then plpb.fit, redo. Now let's add some complex models. First, let's go with the smoothly broken power law. The smoothly broken power law alone has now reduced the CStat from 6,000 to 2,200, which is again a huge improvement. So it means that GRB has complex data and complex models can fit the data better. Let's save these as well. Here we can see that the NAI detectors the data for the NAI detectors is well fitted. However, the LAT data is underfitted. So to compensate that, we can add another power law component in it. And now the CStat has been reduced from 2,200 to 1,100. And if we see the new FNU spectrum, we can see that the extra power law component is now trying to fit the LAT data as well. Let's save these results as well. Okay, let's try it with a black body component. Now here is the first problem we see in our fits. The KT component is standing at 4.48, but if you remember, we set the GBM low energy range to 8 keV or above. So this is an unacceptable fit. We cannot have KT parameter less than 8 or 10. So in order to correct that, we can either raise the KT parameter or the brake energy parameter. So in this case, let's just raise the KT parameter and see. It doesn't work. Let's try one more time. So this is a bit of hit and trial method. You can raise the values from either of the parameter to see what fits the valve. Now let's change this one. So as you can see, I tried several values and finally the value that worked was KT for 200 keV. Let's see the new FNU spectrum. And we also do not have a negative amplitude over here, neither over here, which we do not want. So it is a good fit. Let's save this as well. However, looking at the C-stat, we can clearly see that the blackbody component doesn't really works well. The additional power law component provided a much better fit. Now let's add that as well. Let's do a triple model. Now we can see that the KT component has been reduced to 43 from 150. However, the amplitude is quite low, and we can see a little hump over here which denotes the black body component, and it really doesn't has any significant contribution. However, let's just save these fits. In a similar manner, we will go through the band and componentized model with the power law, black body, and power law plus black body. So let's just do that. We have now fitted all the models in addition to the smooth SBPL band and CPL. We have done double models and triple models as well. Let's just save that. We have not applied the AC correction, so let's just go with no EAC. Let's open the table, edit some columns, and accept. So, okay, we will again add no EAC here. Okay, now let's move towards the effective area correctness. Let's clear this one. Redo last fit. Let's just perform the SBPL PL here. Okay, the C star for SBPL PL is 1172. However, if we add the effective area correctness, now one thing to remember is that the zeroth detector is scaling all other detectors. It means that the NAI4 is being scaled against all other detectors. So in order to scale to BGO, we need the third one, 1, 2, 3, third one to vary. Let's just reset them to default and accept with the third varying parameter. And now we can see that the C-stat is improved from 1172 to 1052, which is over 100 C-stat improvement. And we can also see that the sigma for the BGO detector is now in line with the NAI detectors as well, which is also good. So in similar manner that we fitted the other models before them, we can do the combination of effective area correctness with all of these models as well. And at the end, we can compare the fits file that we are saving now. Okay, we have now also performed the fits with the effective area correctness. So let's just save them. EAC table, edit column. Done. So this was it for the analysis of the GRB. We downloaded the GBM data, the LAT data from the archives and from the GT burst as well. Then we made the XML Sky XML file, and then we made the LAT data using the Fermi tools. We also corrected the GBM files to the correct right ascension and declination using the GBM RSP gen tool. Then we constrained the GBM data in energy and time domains, and finally we have now fitted the models on the data. So this will be it for the series. Thank you for watching. Hope you enjoyed.